Here we are for Honors Physics, Circular Motion, Universal Gravitation, Worksheet 1. We are taking a look at problem 7 on that worksheet, which talks about the Shockwave roller coaster that they used to have at Great America. They actually, that was my favorite roller coaster at Six Flags. And then it was kind of like, the Demon roller coaster there. You kind of go up a hill, a starting hill, and then you go down through, it kind of goes around a curve, and then you go down through 2 loops. And then you go around a little bit, and then you go through like kind of a corkscrew, and then back to the start. Shockwave was kind of like a bigger Demon roller coaster. You had this big hill that you would go up, but then what was really cool about it was when you had the big drop, instead of going straight, it had you curve around and drop, and you kind of flipped around backwards as you dropped. It was really kind of neat. And then you went through like 3 vertical loops and then had a big long double corkscrew part. So it's kind of just like a bigger Demon roller coaster. But anyway, they took that out some years back and replaced it with the Superman roller coaster, which, I mean, I was kind of bummed about losing my favorite one. Superman is so cool. That one, you're like kind of laying down suspended under the track. And you're like laying down, so you're like head first. It feels like you're flying like Superman. It's really cool. So I don't mind that being swapped out. But anyway, so Shockwave. So anyway, so here we go. We're taking a look at the first vertical loop you would flip through after you go down that big drop. And so here you are, and realize at the top you are upside down, right? The cart is rolling on the track, and you're upside down there. And we're doing this. We're thinking about when you're inside the loop at the top. It says the speed of the passengers was 13.3 meters per second, and they experienced a total acceleration of 19.6. Okay, that 19.6 at that point, that is inward toward the center of the circle. So your acceleration is 19.6 meters per second squared down, okay, at that point. It says ignore friction and air resistance, so we don't need any tangential force at that point then. Draw a force diagram for the passenger at the top of the loop. And it says, strangely, you may need to do some calculations here in order to draw the force diagram right. You're like, what? What's going on with that? Okay, let's talk about that. All right. Drawing my sketch. So let's see. We're looking at you when you're at like the top of that loop. So, right? So you're in that car, right? So the person, let's say we're going around this way. Then let's see here. Here's your feet, knee. Maybe you got your arms up. Whoa, as you go around, right? All right. So let's see here. Forces. You say ranged forces. There would be a gravitational force, right? That's going to go from your middle of the person down. Again, we're doing forces on the rider, on the person. And then contact forces. Now, here's the thing. On these roller coasters that have vertical loops, one of the things you'll notice is that they all, pretty much all have, in addition to maybe the seat, but there's a big harness that folds down over your shoulders, right? A big safety harness, all right? And so the point is, then, this harness goes over your shoulder, right? It's the back of the seat, right? At this point, then, we've got a question, and that is, if you're whipping around in the circle, it's possible that gravity pulls you down and presses you against that harness, which then has to push out. It's also possible that you're not actually being pressed against the harness. You're still being pressed into your seat. If you're pressing against the seat, if you're running into the seat's pushing down on you. So the point is, we might be being pressed down by the seat, or we might be being pushed up by the shoulder harness. We're not sure at this point of working the problem which situation we have. So I should probably sketch this twice. And we can talk about which situation we have. It turns out there is a nice, quick, easy way of seeing which of these situations. I don't know why I'm drawing this so much bigger now. Sorry about that. Right? In the shoulder harness. Big shoulder harness going over your shoulder, right? That you might be pressed into the seat. There we go. All right. always the earth pulling down on me here. Excuse me. So the point is, maybe the shoulder harness is pushing up, or maybe the seat is pushing down. We're not sure. So it might be this situation where the seat presses down on us and we have a normal force like that. It might be a situation where the shoulder harness is pressing up on us like that. There's even a special case where you have neither force, but we'll talk about that. So the point is, we're not sure which force diagram it is yet. There is a real quick way of seeing. I'm going to come back to that in a second. I'll show you the shortcut after we talk through this problem a little bit further. So right now, we're not sure which one it is. Well, maybe I should just show the shortcut right away. Let me show you right away. All right. In this case, we happen to know, we were told that the acceleration was 19.6 meters per second squared. That just happens to be the way it was set up for shockwave. And we know that that acceleration has to be toward the center of the circle, doesn't it? So that's our centripetal acceleration. Now, imagine for a second we didn't have either normal force. If there was just gravity pulling on us, pulling us inward, what would our acceleration be? So if the only force was gravity, if we only had the gravitational force, our acceleration would be 9.8, wouldn't it? This acceleration, our centripetal acceleration, is greater than 9.8. So gravity is by itself is not enough force to make us turn that quick, right? This is that force making us bend our path, right? As we whip around the circle, right? You know, we're traveling this way, right? Moving tangent, right? I know I'm drew the path up here, but the path the body's following is like here, right? So our velocity is this way, right? We need to change the direction of that velocity arrow, and we're changing it so quickly, gravity is not enough force to give us that acceleration. So we need more force. So this is the situation we're dealing with, not this. We need to have more force inward. More force in toward the center of the circle than just gravity. So we know that this is the situation we have. If this acceleration was smaller than 9.8, then gravity would be too much force. It would be like trying to pull us down into a tighter circle. We need to cancel out some of that force, then the normal force would go up. If the centripetal acceleration was exactly 9.8, then gravity would be just perfect. It'd be exactly the right amount to give us that acceleration, and the normal force would be 0. And we wouldn't be being pressed into the seat or into the harness. Neither case would we have. All right, so that's the deal there. Okay, so if you happen to know the centripetal acceleration, or if you can calculate it real quick from v squared over r, then you can quickly check to see which force situation you have. Okay, so that is my special tip for vertical loop roller coaster problems. All right, so this is kind of how to tell which situation we have. Okay, continuing on. So for this particular problem with this acceleration, we've got this case. Let's go on to the next part. What would they like us to find? Now that we have a force diagram, they would like us to find the radius of the loop at the top. You notice that this is not a circle. right? The curvature actually changes as we go into this loop. So it's like a bigger radius. This is a chunk of a bigger radius circle here. And then here, it's a chunk of a smaller radius circle, right? This arc. This kind of loop, they do use on roller coasters. There are reasons why they loop it like this. Its special shape is called the clothoid loop, and it's really common on roller coasters. Because this makes a tighter turn, it helps to keep the car pressed into the track harder and keep you in good contact with the track than if we had a big wide circle. We'd have to whip them around faster to stay in contact. So there's good reasons for it. But anyway, I can go through detail on that sometime if you'd like. But we want to find the radius of the loop at the top. So and once we've got that, then they want to know the size of every force acting on the person when they're at the top. That means the one of the force, the size of mg and of n. And they're going to ask how they feel, and we'll go from the apparent weight. Okay, we'll come back to that. So the radius of the loop at the top. You say, well, the way we're going to find the radius of the loop, we know that it comes in to the centripetal acceleration formula, right? It's v squared over r. They told us the acceleration was 19.6, and they told us that the speed at the top of the loop that was given to be 13.3, we know everything we need to know to find that r. So just rearranging that, my radius would be the speed squared over the acceleration. And you say, I'm just going to do it over here. The speed squared, that was 13.3 meters per second, divided by my acceleration of 19.6 meters per second squared. And if I calculate that out, 13.3 squared divided by 19.6, then we get 9.025 meters for the radius. 9.025 meters is the radius of our loop at the top. There we go. Let's see, that was part B. This was part A. Okay, part C. Find the size of every force on the person when they're at the top of the loop. So we need to find the size of n, the size of mg. Mg is really easy, right? You're like, okay, hey, mg. All right. Clearly, that is going to be the mass of the rider, which we're we're told it's a 75 kilogram passenger. Shoo! A second there, I was starting to freak out. Okay, 75 times 9.8. You say, hey, that's 735 newtons. So that's how heavy the person is, how hard the earth is pulling down on them. Now we want to find the normal force. We don't have an equation for normal force. We're going to have to figure that out from the most important formula in physics, Newton's second law, sigma F equals ma. Hey, what coordinate axis are we looking at here? You're like, oh, that's the radial axis, right? That's the center of like this circular path that we're going around in. And so when we do this, the radial axis, we know that the acceleration of the radial axis is always centripetal toward the center of the circle. And when we do the radial axis, we don't have a choice in direction. It's always forces in minus forces out from the center of the circle, right? Centripetal minus centrifugal. So this will be N and mg going into the center. And so I can want to solve for this N. I know M, I know G, I know M, I know AC. I can solve this. N would be MAC minus MG. Okay, so I can do my values here. So mass 75, the centripetal acceleration we were told was 19.6, minus my mass 75 times 9.8. So I can do that calculation real quick. So that's 735. No, it's not 75 times 19.6 minus 75 times 9.8. And I get, oh, look, it's 735 newtons. You say, huh, that's interesting. That came out to be the same size as the weight in this problem. And you say, well, yeah, let's think about this. Notice this acceleration value, 19.6, happens to be, it's the way they did the ride, exactly double 9.8. So you need exactly twice the force as you would with just your weight. So it's like your weight and then another force just as big to accelerate you twice as fast as gravity accelerates you. Make sense? So N is actually the same size as mg in this case. It just happened to work out that way, the way they did the shockwave ride. All right, so which brings us to the last part. Okay. Oh, this was this is part C that we're doing here, finding those sizes of the forces on the person. So they say, hey, does the passenger feel like they're being pressed into their seat, or do they feel like they're being held in place by the harness at this point? We sort of answered that here. We said, hey, you are being pressed on by the seat. Gravity by itself is not enough force to make you turn this quickly, right? To accelerate inward that quickly. We needed extra force inward, and so the seat is going to have to press on you. Remember, we're moving along tangent to the circle. If it wasn't for that seat being there, you just like kind of keep going straight, just go flying off, right? So that seat has to press in on you to help gravity out to make you turn that quickly, right? If we were going slower, then the gravitational force would be more force than we needed. It would give us an acceleration that's 9.8. If we were accelerating, if we needed to accelerate slower than 9.8, gravity would be too much force. We'd have to cancel out part of it with that. And the only way to push up is to have that shoulder harness press up on you. And so then we'd be going, so if we're going really kind of slow through the loop, we would need more force up to hold us into the seat. If we're going super fast, actually, we're running into the track. Right, we're trying to keep going straight. We're running into the track, right? Or in this case, you're running into your seat, and so the seat pushes back down. All right. So you feel definitely like we're pressed. We're being pressed on by the seat, and so you feel, hey, the chair is pushing on me. You kind of feel almost like you're being pressed into the seat. All right. You're really running into it as it's trying to turn into you. Yep. So part D. We have this normal force from the seat, so we feel like we're being pressed into the seat. The passenger would feel that way because the seat is pushing on them. Okay. Part E asked, what is the perceived weight or apparent weight of the passenger? How heavy does that person feel like they are? Okay, we talked about this a little bit on the previous problem, on problem 6, on the Ferris wheel problem. The idea of apparent weight or perceived weight, that's the size of the force that is supporting you. That surface is supporting your weight. You see, the thing is, in this case, you're being pressed into by the seat, right? To you, you can't really feel the difference between gravity shoving you into a chair or the chair pushing into you. So at this point, you feel like you are being pressed into the seat. And so you actually feel like down is that way, and the seat is pushing up on you. If it wasn't for that seat being there, your velocity is like this. You would continue going that way, and the seat's pressing you in. So imagine what would happen if we were traveling along this, right? You say if you were to let go of a coin or something, the coin would want to keep going tangent, right? And when I'm at this point, the coin would want to keep going sideways. We would curve in. It would look like, so here's the seat, maybe, yeah. And then here I am upside down, right? If I let go of a coin at that point, the coin would want to keep moving. So at the point where we're right at the top, the velocity is sideways, the coin would want to keep moving sideways. There wouldn't be a force shoving on it. But I'm moving and turning, and I would turn into it. From my point of view, as that coin tries to keep going sideways, but I turn into it, it would look to me like the coin fell to my lap. In fact, that normal force is the same size as the gravitational force on me. Well, isn't that how big it would be if I was just sitting on the ground and the ride wasn't moving? I would be pressed into my seat by a force equal to my weight, and the seat would push up with a force equal to my weight. So to me, this feels identical to just sitting still on the ride when I'm at that point. For that instant, the force on me is the same as if I was just sitting still on the ground. So I feel like I am my usual weight All right. All right. My apparent weight is that support force pressing on me. It's just the normal force. That's 735 newtons, which happens to be my usual typical weight. Okay, so that force surface pressing into you, that is your apparent weight. How heavy you feel like you are is how hard your that surface is pushing back on you. That's how you calculate an apparent weight. What would happen if we whipped you through this ride slower? Well, then you wouldn't need as big of an acceleration, so you wouldn't need as much force in. That normal force would get smaller and you would feel like you were lighter than usual. If you go a little slower, the normal force gets smaller, smaller, smaller. There's a point where the speed you're traveling at would be just right so that your centrifugal acceleration would be 9.8. Then gravity would be all you would need to give you that acceleration. The normal force would be 0. And you would not be being pressed into the seat anymore or being pressed in the harness. You would feel like there's no normal force in it at all. You would feel like you were weightless. You're not being pressed into anything. Like for an instant there, you'd feel like you were weightless. There's a lot of roller coasters that try to bring you close to that point at the top of a loop, because it's kind of a neat sensation. What would happen if we went really slowly through the loop? Well, now gravity's trying to accelerate you at 9.8. And that would be bigger if that was bigger than the centrifugal acceleration we need, because we're going super slow, right? Centrifugal acceleration just speed square root of r. If I went really slow, that centrifugal acceleration I would need to make that turn I'd be turning more slowly. It'd be a small AC. If it was less than 9.8, gravity's too much force. It wants to accelerate me at 9.8. So I would need to cancel part of it with the normal force out. I would feel myself being pressed into the harness, and however big that harness force is on me, that's how heavy I'd feel like I was being pressed in. So anyway, good enough. That's it. That's problem 7. A good bit there about perceived weight and apparent weight, which is something that you can expect us to ask you about in the future, because it's kind of a neat sensation to think about how that feels. And there's some cool applications of it. Okay, that's problem 7.